Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
The discovery of the neutron happened in the year 1932 by James Chadwick. Before this, scientists knew only of protons and electrons as the prevailing subatomic particles. However, the biggest challenge was knowing how these two particles were arranged within the atom with respect to each other. The following tutorial discusses the various models of the atom proposed by the following renowned scientists: J.J. Thomson, Antaro Nagaoka, Ernest Rutherford, and Niels Bohr. The Thomson's model. Based on the findings outlined in Video 1, the discovery of electrons and protons, Thomson in 1904 proposed his model of the atom. He suggested that the atom was a positive sphere with electrons embedded in it like the way raisins are in a bun. So quickly, this figure here depicts the Thomson's model. So this is a depiction of the Thomson's model. Here is the positive sphere, and these are the embedded electrons in it. Electrons are embedded in it in a similar way that raisins are in a bun. So this is the Thomson's model, the Nagaoka's model. In the year 1903, Japanese scientist Hantaro Nagaoka proposed a model of the atom as comprising of a spherical positive center surrounded by a ring of electrons that mimics the planet Saturn. He was the first scientist to propose a model of the atom with a nucleus. However, after closer scrutiny, his model did not conform to later more scientifically sound discoveries. It was thus shelved. So here is the model of Nagaoka. It's called the Saturnian model. Here you have the massive positive sphere that he speaks about, and he says around that are the electrons that are arranged in this ring-like structure that has a similarity to the planet Saturn. This brings us to Ernest Rutherford's nuclear model. The model of the atom proposed by Ernest Rutherford was the result of his investigation of the model proposed by J.J. Thomson. According to the model proposed by Thomson, every atom of an element should have a uniform composition in terms of its charge and particle distribution. Determined to test the validity of Thomson's model, Rutherford will use the newly discovered alpha particles produced from radioactive materials in this endeavor. Each alpha particle is composed of 2 protons and 2 neutrons and is ejected from radioactive sources with a considerable amount of energy, making it capable of penetrating a thin gold foil. Rutherford reasoned that if alpha particles are shot at one point on a gold foil of a few atoms thick, and they pass through, then the same should happen if they're shot elsewhere on the same gold foil. So this figure here demonstrates Rutherford's prediction of the movement of the alpha particles through the gold foil. So what we're seeing here is this. These are the replicas of the atoms proposed by Thomson. If you examine each one of these closely, you can see that there's uniformity of the charge distribution here. And not only that, we do not see any part of an atom there where there's any aggregate of materials. So we're assuming that each part of the atom is of uniform density. What Rutherford is saying is that if the alpha particles are shot here and they pass through there, they should pass through anywhere else because each of these atoms here is identical to the other. Okay, now that was his prediction. Let us see what he did and what actually happened. First of all, he needed a source of alpha particles, and these were provided by a radioactive source that was kept safely by the lead container here. In front of that is a screen with a small hole that allowed only a fine beam of the alpha particles to pass through. This here is the gold foil that was under investigation. What Rutherford did was this. He placed phosphorescent screens in front and back of the gold foil to monitor the movement of the alpha particles as they exit the foil, or for any possible rebounding. That's why he had these in front here. Whenever an alpha particle impinges on the screen, it gives an instantaneous glow, like this one here. Rutherford used the positions of the glows on the screen to determine the movement of the alpha particles after they were shot at different points on the gold foil. So here we can see, based on the position of these glows here, Rutherford was able to make some conclusions, as depicted by this figure here. What he was saying that the majority of the alpha particles passed through the gold foil unaffected, but only a tiny few of them were deflected sideways, and a few of them even rebounded. So what did he conclude? He concluded that the model of the atom proposed by Thomson was not accurate, since it could not explain these movements of the alpha particles. Now, I'm giving you a picture here for you to see the comparisons of Thomson's model here. And this figure here represents the model of the atom proposed by Rutherford. So this one here could not explain why you're having the deviations, the deflection sideways, and the rounding of the alpha particles. But the one that is proposing now seems to be more plausible in terms of explaining why the alpha particles demonstrated such type of movements. So this is what Rutherford is saying, according to his model of the atom. He's saying that the alpha particle, when they approach the gold foil, must have encountered something that is massive and also positively charged. And that is why the alpha particles, some of them were deflected sideways. The alpha particles being positively charged, as they approach this positive nucleus here, sideways, of course, positive charge here will repel positive charges. You had these sideways deflection here. And of course, this one that rebounded was due, he said, to a direct impact on the nucleus there, which he said was positively charged and is solid. He's saying the reason why most of the alpha particles went through freely unaffected is because only a small part of the atom is occupied by the nucleus, very, very tiny part, and the rest is empty space wherein exist the electrons. So most of the atom, he's saying, is empty space, but in this middle of it is where you have the nucleus that is positive in nature. This is the model proposed by Rutherford, and it's all summarized here, and the deductions, whatever he made there, are contained there too. So this is a nuclear model as proposed by Rutherford, and it was the result of him trying to see whether or not the model proposed by Thomson was correct. One thing more to know, I alluded to that already, is the scientists believe that the nucleus inside here is extremely tiny compared to the rest of the atom. Some people even went on to say it's like putting a little ball in the center of a football stadium, the ball representing the nucleus of the atom, and the rest of the stadium there is how large the atom is. So, well, thank you for listening, and I hope that was useful. Our next lesson will deal with the work of Niels Bohr.